My talk will be about parameterizing spaces of positive representations. This is a joint project with Guichard and A Wienhard. And here's my plan for the talk. So first of all, I will give you some motivation, introducing the higher Teichmüller theory. Then I will discuss a little bit the positivity in Lie groups on one example. And then I will give a general construction, but very hand-wavy. And then I will define framed and positive representation of a surface group into a Lie group. And finally, I'll present you the main result, our main result about the parameterization of space of framed positive representation. So let's get started. So, wait, yeah. So what is the higher Teichmüller theory about? So for us today, S will be an oriented surface, so we fix an orientation. So a surface for me is a two-dimensional real manifold of finite type and of negative Euler characteristic. So in this case, the fundamental group of S, which I denote by P1 of S, is a finitely presented group. And we also take some Lie group G, usually reductive or semi-simple, and then we can consider the space of all homomorphism of P1 of S into G, modulo conjugation by G, and this space is usually called character variety or representation variety. This is a topological space. For example, you can take the compact open topology. And okay. And the higher Teichmüller space is a subspace of the character variety, which is the union of all connected components and consists entirely of injective representations with discrete image. Sometimes one also say it like discrete and faithful representations. And you can ask why these spaces are called higher Teichmüller spaces. And in fact, if G is the simplest possible semi-simple Lie group PSL to R, then the character variety has two connected components and consists entirely of injective representations with discrete image, and one of them can be identified with the usual Teichmüller space using the holonomy representation. So the Teichmüller space is the space, essentially, it is a modular space of hyperbolic or complex structures on the surface S. And the second connected component, which consists of discrete and faithful representation, can be identified with the Teichmüller space of S, but with the opposite orientation. And the higher Teichmüller spaces are essentially generalizations of these spaces for groups of higher rank. And the important remark is that higher Teichmüller space exists not for every group G. For example, if the group G is complex Lie group, for example, PSL2C or SP2 and C, then the character variety is usually connected. So there are no interesting connected components. And the important question is to characterize Lie groups which admit the higher Teichmüller spaces. And there are two well-known families of examples of higher Teichmüller spaces. The first family is the family of split real Lie groups. If you don't like split real Lie groups, you can just think of SLNR, SP2NR, SONN, SON+1. So essentially every complex Lie group admits a split real form. And in this case, higher Teichmüller spaces are so-called Hitchin components. And the existence of these Hitchin components is closely related to the notion of total positivity for split real Lie groups. And this notion is very well studied. It was introduced, especially for GL and R. It was introduced in 1930s, I think, and studied by many researchers. Here I just mentioned several of them, like Lustzig, Fock, Goncharov, but there are plenty of people who studied total positivity. And the second family of examples are so-called Hermitian Lie groups. If you don't like Hermitian Lie groups, you can just think on SP2NR or UNN. But the Hermitian means essentially that the Riemannian symmetric space associated to the group G is not just a Riemannian symmetric space. In fact, it is a complex manifold. And even more, it is a Hermitian manifold. And in this case, higher Teichmüller spaces are so-called components of maximal representations. And the existence is closely related to the notion of maximality, which was introduced and studied by Mark Berger, Alessandro Iozzi, Anna Wienhard, François Laborie, and many other people. And 2019, Guichard and A Wienhard introduced a new notion of positivity, they call it theta-positivity, for a much larger class of semi-simple Lie groups. So that the first and second examples are just special cases of this more general notion of positivity. And they also gave new examples. So first new family of examples is the group SOPQ for P smaller than Q. And the fourth family of examples is this exceptional family of exceptional Lie groups. Okay. And now I'll illustrate a notion of positivity on this second example on maximality for SP2 and R. So I believe many people already know about like total positivity. So I'll illustrate it on this example, which is less well known, say like that. So, and I see the group SP2 and R as the group of isometries of the vector space R to the power 2n equipped with the standard symplectic form, which has this form. And I also fixed the standard symplectic basis, E1, En, F1, Fn, which satisfy these conditions. And then every generic enough matrix A, symplectic, can be decomposed as follows, as a product of three matrices U minus, D, and U plus, where U plus is the block upper triangular unipotent matrix. And by condition to be symplectic, this matrix A in the upper right corner is always symmetric, real. So the same for U minus, it's lower triangular unipotent matrices, block unipotent matrices. And D is the block diagonal matrix. On the diagonal, we have A and A transpose minus 1. This is again the consequence of the condition for this matrix to be symplectic. And then inside these unipotent subgroups U plus and U minus, there are nice so-called positive semigroups, U plus minus positive. Here I write this for U plus, but you can imagine how it looks for U minus. So these are all the block unipotent matrices, so that this symmetric matrix A is not just symmetric, it's symmetric and positive definite. And you can easily check that this is indeed a semigroup that's closed under multiplication. And then this notion of positivity reflects nicely in the action on flag variety. In our case, the flag variety will be a Lagrangian Grassmannian. So this is the space of all n-dimensional subspaces in the R2n, so that our symplectic form vanishes. And since we fixed a basis, a symplectic basis, we can define two standard Lagrangians, which are the span of the first n vectors in the basis and the span of the last n vectors in the basis. And moreover, the group SP2 and R acts transitively on the flag variety. And we can also compute the stabilizers of these two standard Lagrangians, and they are these parabolic subgroups, so upper triangular, lower triangular matrices, block upper triangular, block lower triangular matrices. And in fact, they are semi-direct products of D with U plus and U minus. Which we already have seen before. So in this sense, we can identify the flag variety with the homogeneous space SP2 and R modulo P plus or P minus. But in fact, this is not just a homogeneous space. This is a compact Riemannian symmetric space. So it has much more structure. And now, if you have two Lagrangian subspace, we say that they are transverse if they are in the direct sum. And if you have a sequence of Lagrangian subspaces L1, Lk, then we say that this sequence is positive if there exists an element G in SP2 and R, and there exist elements U1, UK minus 2 in the positive semigroup U minus positive, such that if we apply this element G to the sequence, then the first Lagrangian subspace goes to L0, the last one goes to L0 opposite, or to the second standard Lagrangian, and this intermediate K minus 2 Lagrangian subspaces goes to the U1, L0, U1, U2, U1, L0, and so on, Lk minus 2, U1, L0. And I'll give you an example how it works. But first, I would like to notice several facts. So, for example, every two Lagrangian subspaces in the positive sequence are transverse. Then these elements U1, UK minus 2, they are uniquely defined, but only up to conjugation by an element of D. So since this, the group D acts on U plus or U minus by conjugation, and in fact it acts also on U plus and U minus positive by conjugation. And the last fact is that the positivity of the sequence is invariant under the cyclic permutation. So you can permute the sequence cyclically and it stays positive. And the baby example is, of course, if n is equal to 1, so our group is sp2r, which is SL2r, SL2r, and the flag variety is just the real projective line. And then the sequence of positive sequence of Lagrangian subspace is just the sequence of lines in the RP1. And you can see that essentially on this picture, the positive sequence means that we start at L0 and then going in the increasing order to L0 opposite, to the second standard Lagrangian subspace. So you can essentially see that the positive sequence is just the increasing sequence. And by this third remark, you can also see that it doesn't matter in which Lagrangian subspace you start. It is kind of cyclically ordered. So if you start instead of L1 by L2, but you can still kind of renormalize the sequence so that it stays positive. So for SL and R, positivity essentially means cyclically ordered in RP1. Okay, and how it works in general? In general, you can just pick one semi-simple Lie group and fix a parabolic subgroup inside G. So parabolic, if you don't like parabolic subgroups, you can just think of block upper triangular matrices as we have seen for sp2 and R. Then this parabolic subgroup can always be decomposed by the Levy decomposition as the D, which is a reductive subgroup, which you can think of like a block diagonal matrix, and U, which is a block unipotent, say, upper triangular, lower triangular matrix. So you can see on this illustration how it works, this decomposition. And then we say that the group G admits a P positive structure if there exists a semi-group U positive inside U, such that first U positive must be invariant under the action of D0. So D0 is the connected component of the identity inside D, inside this block diagonal group. So the entire group actually does not have to act on U positive, but the component of identity always acts. And the second condition is essentially that our U positive is as much semi-group as possible. That means that if we take two elements in the topological closure of U positive, then their product is equal to identity if and only if both of them are the identity element. And if the group admits a P positive structure, then we can define the flag variety as the homogeneous space G mod P, and then play the same game. We can define positive sequences exactly in the same. We can just literally translate the definition I gave for the symplectic group in these terms, just replacing the corresponding groups by these more general groups. And the fact is that the groups with positive structure are classified. This is the fact which is proven by Olivier Guichard and Anna Wienhard. And these are exactly these four families which I mentioned at the beginning: split real Lie groups, Hermitian Lie groups, SOPQ, and the exceptional family. Okay, and now we can go to representations. So now we take a surface as before, and we will discuss only the punctured surfaces. So that means that our surface is the closed surface, so the compact without boundary, and we remove finite collection of points, P1, Pk. In this group, the fundamental group of our surface is always free. And if we pick some Lie group, G, say with positive structure, then the character variety is just G to the power n, because the group is free. So if G is connected like sp2 and R, then there are no there's only one connected component, so we cannot find anything interesting. And moreover, P1 of S does not depend very much on S, because there are many punctured surfaces with the same fundamental group. So to find interesting connected component, we add some more structure. And this will be a framing. But first, let's discuss a little bit the peripheral elements of the fundamental group. So an element of P1 of S is called peripheral if it can be represented by a loop going around exactly one puncture. So on this picture, you can see like blue curves are peripheral, red curves are not peripheral. So the space of peripheral elements I denoted by P1 per S. So this is not a group. This is just a set, but this is a very nice set. This is a normal subset. That means that P1 of S acts on P1 per S by conjugation. And if we now take the flag variety associated to G with the parabolic subgroup P and pick one representation rho, then we can define the following map. So a map F from the space of peripheral elements to the flag variety is called a framing of rho if it is rho equivalent. That means if we pick an element of the fundamental group and we pick an element, a peripheral element, then the flag associated to the conjugated element, alpha, gamma, alpha minus 1, is just the flag associated to gamma, and then we apply rho of alpha, which acts naturally. This is an element of the group G. And from this equivariance, we can easily deduct the invariance property. That means that if we take the flag associated to a peripheral element gamma, then it is invariant under rho of gamma. You can just take alpha equal to gamma. And this is quite important property, which we use to parameterize the representations. And a pair rho F is called the framed homomorphism is F is the framing of rho, and then we can define the space, like framed character variety space of framed homomorphisms up to action of the group G. So G again acts on representations by conjugation, and it acts on framing because it acts on the flag variety. And then we can define the positivity of a framing. So if for there are many ways to define positivity for a framing, but so I'll use the simplest one, but for this we need to use ideal triangulations of surfaces. So we pick an ideal triangulation. So an ideal triangulation is a triangulation such that all the vertices of the triangulation are punctures. And if we pick an ideal triangulation, then we can pick an ideal quadrilateral. That means like two triangles which share an edge. And then we say that the framing is positive if for every quadrilateral, so for every quadrilateral, you can define quadruple of peripheral curves, peripheral elements of the fundamental group. Then the framing, so we have our framing gives us four flags in the flag variety. And then we say that the framing is positive if for every quadrilateral, this quadruple of flags is positive in the sense we have seen before. And the fact is that actually this definition does not depend on the triangulation. You can pick any triangulation, and if the framing is positive for one triangulation, it will be positive for another triangulation. And moreover, this okay. So and now if we say that a homomorphism is positive if it admits a positive framing, and the fact is that actually this property to be positive is an intrinsic property of a homomorphism. So that means that if one framing, if our representation admit one positive framing, then every framing of our rho will be positive. So it is not unique, but all the framings will be positive in this sense I defined before. And now we can define the framed positive character variety, so the space of all positive framed representations. Again, G acts by conjugation on rho and by the natural action on F, and this action preserves the property to be positive. And our theorem with Guichard and A Wienhard says that this representation, this space of representation can be nicely parameterized. So this space is homeomorphic to the following space. So we take this positive semi-group to the power minus 2 Euler characteristic of S. So the Euler characteristic of S was negative, so this number is positive. Then we multiply with d0 to the power 1 minus the Euler characteristic of S, and then we divide out the action of d0 by conjugation. So this d0 is the maximal subgroup inside D which preserves this U positive by conjugation. So as we have seen, D acts on U by conjugation, but it shouldn't act on U positive. We know that the connected component of the identity act on U positive, but sometimes a larger group can act by conjugation on U positive. So this D0 is this maximal subgroup. So sometimes it is just the component of identity. Sometimes it is the entire group D. Okay, so I have a little bit time so that I can explain a little bit how these parameters work. So the first parameters, so this power 2 minus 2, the Euler characteristic of S, is exactly the number of triangles in the ideal triangulation of the surface S. So as we have seen before, so we have triangles, and then if we have one triangle, then we have 3 flags, and then we can put the first flag to the first standard flag, the third flag we can put to the second standard flag, and then there is the second flag, which as we have seen, that is like U times the first standard flag, and this U we associate to this triangle. And you can see, so essentially the first part of the parameterization is that for every ideal triangle we have an element of U positive. And the second factor is slightly more complicated. Essentially, this power is the number of generators in the fundamental group. That means that to some extent we can say that additionally to this information of U positive in every triangle, we need a representation of the fundamental group, but in a smaller group, in this diagonal group D0. And then this D0 acts by conjugation. And as we have seen, these parameters U, they are well defined, but only up to conjugation by D0, as we have seen before when we discussed the maximal, the positivity for sp2 and R. So since these elements U are not well defined, they defined only up to conjugation, so we need to divide out this action of D0. So this is where these parameters come from. So, okay, my time, so probably I need to stop now. And yeah, I thank you for your attention. If you have questions, I'm happy to answer them.
Thank you very much. Let's thank the speaker with some virtual applause. Are there any questions for the speaker? Yeah, I guess there's, besides the puncture case, what other cases can you consider in the chat?
Yeah, we can consider, our theorem actually works for more general case when we consider ciliated surfaces. So not just punctured, but also like surface with boundary components, so that the punctures sit on boundary components. And in this case, the construction is slightly more complicated. Then the property of positivity is not the intrinsic property of the homomorphism. There might be homomorphisms which admit positive framing and non-positive framing. The only case we cannot cover is the case of closed surfaces. So if we have no punctures, no boundary, nothing, because then we cannot consider ideal triangulations. And in fact, I believe that this case is much more complicated. Yeah.
Okay, thank you. Are there any other questions for Eugen?
How about the pinched surfaces? Could you cover these?
Thank you. New details on serious contract for the beauty.
Surfaces.
The former mayor attending the Toronto Blue Jays farm teams.
Okay, this is a very good question. So I haven't thought about this. Yeah, but if you, okay, I'll not say anything wrong. So I don't know. I haven't thought about this.
Okay, thank you very much. Any other questions? Oh, well, if not, let's thank Eugen again. Very nice talk.